In this video, we want to talk about the fundamental theorem of algebra. Now, to get us started, we want to start going back to our idea of looking at polynomials a little bit. Now, we've talked about how to graph things on the calculator, but one of the problems with graphing things on the calculator is if you don't know what something looks like, you have no way of knowing if you've graphed it correctly or not. So what we want to talk about is a little bit about knowing basic shapes, and you've seen these before. If we have quadratics, the basic shape of a quadratic is our u. If the a, the number in front of the x squared, is positive, our quadratic opens up. If the a is negative, it opens down. Now, these quadratics can be moved around. As we looked at our parent functions, these could be up or over or down or anywhere in our graph. You know, they may cross the x-axis at two places, they may cross at only one, they may not cross at all. All of those are possibilities. If we have a cubic, a very basic cubic would just kind of look like this. It would come up, kind of sort of level off and continue up. That's if the a is positive. If the a is negative, it would come down, kind of level off, and go down. Now, as it gets more advanced, and when I mean advanced, more difficult, these A's, B's, C's, and D's change a little bit. What would happen is the graph will get these peaks and valleys in them. And the same with the negative going down. So as we look at that, we think about like our max and minimum yesterday, a cubic is going to have those. Okay, as it gets a bit more advanced. If we have a quartic, that's a fourth degree. Now, a basic fourth degree will look just like a quadratic. It may be a little narrower, it may not, depending on what a is. But you can't really tell by just looking at a graph if it's a quadratic or if it's a fourth degree, a basic one. Now, it can be a little more advanced, and it may kind of have this bump in the side, or it could open down and have that little bump out to the side as the B's, C's change. But it could get even more advanced, and you could actually have kind of double peaks and valleys going up or going down. So there's an example of what a quartic, a fourth degree, could look like. A lot of different shapes depending on how many peaks and valleys are in the graph. As we go to higher degrees, let's say a fifth degree, what happens is we get more peaks and valleys. Now, a fifth degree could look just like a cubic, or even a more advanced cubic. It may just look like that. However, also with the right A, B, C's, D's, E's, F's, you could get even more peaks and valleys. A sixth degree is the same way. It could look just like a fourth degree, or you could get an extra peak and valley. One of the important things to notice, though, is if you have an odd degree, the ends of your graph, think end behavior, are always opposite. One's going up, one's going down. Now, they may be the other way if it's a negative A, but when it's an even degree, the ends are always going the same way, both up or both down. Now, as we look at these, there's a couple of things with different kinds of roots that we can have. If we have something like x minus 2, that has a x-intercept, that has a root of just 2, and it just goes through the graph. If we have a root of negative x minus 2 quantity squared, now that's a double root. And it kind of comes down and touches on the same side. If we had an x minus 2 cubed, notice it comes up, all these have a root 2, kind of levels off. So what does that mean? Well, what this means is if I looked at an example here, let me just kind of show you what these pictures represent. And I had a function. So let's say I had y equals x plus 2. Well, that's at 2. That means I know it crosses at negative 2. If I had x minus 1 squared, that means this is also a root, but that's a double root. I know at negative 2, it's just a single root. just goes through. I know at negative 1 it's a double root because it's squared, so it's going to look like this. My rest of my graph, the basic shape then, and then so I know where it is exactly. It's going to come something over here, something up here, something down here. I use dash because the only part I really know for sure is right here is a single root and right here is a double root. So I can get that basic shape by knowing that. Now, we're going to look at the actual fundamental theorem of algebra. Now, before we get to the fundamental theorem of algebra, let's talk about the fundamental theorem of arithmetic first. The fundamental theorem of arithmetic says every number has a unique prime factorization. So if we look at a number like 6, think factor tree, that is 2 times 3. If I had a number like 12, I could take 2 and 6, 2 and 3, so I could say that is 2 times 2 times 3. That is the fundamental theorem of arithmetic. Now, that's important just to understand the idea of that kind of basis for a lot of what we do in arithmetic. We don't think about it, but that's it. Now, one interesting thing about this, because of this, 1 is not a prime. 1 is not a prime number. And the reason is this. If 1 was a prime number, I could take 2 times 3, and I could multiply it by 1. And I still get 6. And I could multiply it by 1 again, and I still get 6. And I no longer would have a unique prime factorization, because I can add 1 over and over and over to get an infinite number of different ways of getting 6 with prime numbers. So because of that, 1 is not a prime number. Now, my fundamental theorem of algebra says this. In a complex number system, if p of x is a polynomial of degree n, so I have a polynomial of degree n, then I have n roots. We've talked about that already. If I have a cubic, I have 3. A quadratic, I have 2. A fourth degree, I have 4. We've already talked about that. But this idea of the complex roots, we need to talk about a little bit more. If I consider a cubic, I think we know our graph now. It looks like that. So how many roots does it have? It's got to have 3. But I only have 1, you might say. 1 right here. That tells me I only have 1 real root, and the other 2 have to be complex. Have to be imaginary. Now, I'm always going to get 2 imaginary, or 2 complex. And the reason is because of the conjugate theorem, which says irrationals and complex roots always come in pairs. So if I have the square root of 2 as a root, I have to have negative square root of 2 as a root. If I have 5 minus 2i as a root, I have to have 5 plus 2i as a root. They always come in pairs, as you see here. I can't just have 1. Now, what we can do with that, if we look at this, find a quadratic with integral coefficients, that just means integers in front of the variables, with the root of square root of 3. Well, we know if our root is square root of 3, our factor would be x minus square root of 3. Remember, when we've looked at before, if I have 2 and negative 3, my factors would be x minus 2, and I'm going to write it this way for now, x minus a negative 3. Well, minus a negative is plus, so we get x minus 2, x plus 3. So it's important to understand our factors is always x minus the root. So if I have square root of 3, I get x minus square root of 3. But to get a quadratic, I need another factor. Well, if square root of 3 is a root, then I know negative square root of 3 is a root. And I can get x minus the square root of 3, x plus the square root of 3. Now, technically, we could multiply this out in FOIL. I'm not going to worry about it. I'm interested in you just writing down the factors. That's all we're interested in today. Let's say we have a quadratic with integral coefficients with the root of 4 plus I. Well, if 4 plus I is a root, then so is 4 minus I is a root. Now, if I write these factors, I get x minus 4 plus I, and I get x minus 4 minus I. So there would be my two factors. Once again, I can multiply it out if I wanted to, but we don't want to. What if I have a cubic? Now I need 3. Well, I have minus 2 and 3i. So I need 3 factors. Well, I have x plus 2, x minus 3i, but what is my third? Well, if I have 3i, I have to have minus 3i. So I get x minus a negative 3i. Or I could rewrite that as x plus 3i. So there are my 3 factors for my cubic. All right, we're ready for the homework on fundamental of algebra.